Hello, you've got Sidhanth here, and today we're going to talk about two-dimensional expansion of random geometric graphs. And this is based on joint work with my wonderful collaborators Siqi, Tselil, Schramm, and Elizabeth Yang. So let's first talk about the notion of spectral expansion. So let G be an n-vertex graph. Then all of its eigenvalues, namely the eigenvalues in the normalized adjacency matrix, lambda 1 through lambda n, lie in the interval between -1 to 1. And the spectral expansion of the graph is the quantity, which is the second eigenvalue of the normalized adjacency matrix. And finally, we call a graph a spectral expander if the second eigenvalue is non-trivially bounded away from the first. That is, if this gap between the first and second eigenvalue is at least a constant epsilon. So some nice properties of spectral expanders is that random walks mix rapidly, and such graphs have no sparse cuts or no dense subgraphs. And these nice properties lend them to applications in various areas of theoretical computer science, such as correcting codes, pseudo-randomness, fault-tolerant networks, metric embeddings, approximation algorithms, and more. So I defined what a spectral expander is, but do these actually exist? And turns out, spectral expanders are everywhere. So in particular, if G is a random deregular graph, then with very high probability, it's actually a really good spectral expander. In fact, the second eigenvalue is at most this quantity 2 square root d minus 1 over d, up to an additive term that goes to 0 as the number of the vertices in the graph goes to infinity. And this is the best possible among the family of deregular graphs. Further, in addition to knowing that random graphs are good spectral expanders, we also have a wealth of explicit constructions. There's various Cayley graph-based constructions, such as the Ramanujan graphs of Lubotsky, Phillips, Sarnak, and Margulies. Then there's combinatorial constructions based on this exact product. And there's also this particular method of interlacing polynomials due to Marcus Spielman Srivastav, which was made constructive by Michael Cohen. And some of these randomized constructions can also be de-randomized to give you deterministic ones. Okay, so, but in the title of the talk, we said we were going to talk about two-dimensional spectral expander. So what is two-dimensional spectral expansion? Once again, you have an n-vertex graph, G, and now we're going to need this notion of a link. So given a vertex V in the graph, the link is the induced subgraph on the neighborhood of V. So here think of V as the marked green vertex. The pink vertices are the neighbors of V. And as you can see, the induced subgraph on the pink vertices is a 5 cycle. So we say that the link of the green vertex is a 5 cycle. Okay, so now what does it mean? Now that I've described what a link is, what does it mean to be a two-dimensional spectral expander? So in a 2D expander, we acquire that the graph G itself is an expander, and further, every link in the graph also must be a pretty good expander. And here, by a pretty good expander, what I mean is the second eigenvalue of the link must be at most half minus a constant. So for expanders, we need the second eigenvalue, the whole graph is 1 minus a constant. But here we need that every link is at most half minus a constant. So what is the significance of this number half? And the reason is due to this particular theorem called the trickling down theorem, which can be seen as far back as in the works of Garland and Zhuk, but the modern version is attributed to Oppenheim. So it says, if every link in a graph G that is connected has spectral expansion lambda, then the whole graph is a lambda over 1 minus lambda spectral expander. And you see, when lambda is less than a half, then you actually know that the expansion of the whole graph G is actually bounded away from 1. So in particular, expansion of the graph G, which is a very global property, actually has a very local witness via the expansion of links. And the nice thing is that in addition to implying expansion of links, it also implies rapid mixing of a particular walk on the edges of the graph, where you go from an edge to a triangle that contains the edge, and then to another edge that is part of this triangle. But we won't discuss this too much today. Okay, so the fact that global expansion can be witnessed locally is also something that is pretty useful in various TCS applications. For example, you can use them to construct agreement expanders. This notion of links and expansion of links implying expansion in some global structure has been very fruitful in the area of sampling algorithms. And we have these new set of techniques called spectral independence. And recently, objects such as these higher dimensional expanders were used to construct locally testable codes and also quantum low density parity check codes. And hopefully in the years to come, we shall see many more applications. Okay, so I described what a two-dimensional expander is, but once again, the question is, how do you actually construct them? And one could try to take a leaf from the story for just standard expanders, and you could try asking, let me sample a sparse random graph. Is it going to be a two-dimensional expander with high probability? So maybe the particular model that you look at is you simply take an Erdős-Renyi graph, and the thing that happens for Erdős-Renyi graphs is that once the degree is as large as omega square root n, that is, you have an edge, you have a very dense edge set, then you actually do see a two-dimensional expander. But if the average degree is any smaller than square root n, then all the vertex links are disconnected with high probability. Note that this is in stark contrast with the situation for standard expanders, where Friedman's theorem tells us that even when you take a random 3 regular graph, you already have pretty non-trivial expansion. And over the years, there have been several other models for these higher dimensional expanders that have been proposed. There is one by Laniel and Meshulam where you consider every triangle that can possibly occur and add it with probability p. And there's a few others, and all of them run into this barrier that once the degree is smaller than square root n, then the links are actually disconnected, let alone expanding. So then you could ask, okay, a random graph is unable to achieve a two-dimensional expansion even when the degree is, say, as large as n to the 1/4 or even n to the 0.49. So do two-dimensional expanders actually even exist when the degree is small? And turns out they do. Turns out there are sparse constructions of high-dimensional expanders where the degree is constant. The first ones of these are due to Cartwright, Solis, Zhuk, and Lee. And there were later other constructions by Lubotsky, Samuels, Vishney, Kaufman, Oppenheim, and O'Donnell Pratt. There are certain combinatorial constructions too, which are based on choosing an expander and taking some kind of graph product, but they don't actually achieve second eigenvalue less than 1/2 in the links. Okay, so at this point, there seems to be this big discrepancy between the explicit constructions that we know via algebraic and number theoretic techniques, wherein you are actually able to construct constant degree high dimensional expanders, versus all natural random models we know seem to get stuck at this square root n barrier for the degree. That is, you need the degree to be at least root n in order to see any kind of high dimensional expansion. So, what is a random model that can actually break the square root n barrier? This is the motivating question of our talk. And here is sort of a blueprint of a model. You could choose, you could take some metric space, and the vertices in your graph um, are, say, going to be independently drawn points in this metric space, and you choose edges based on proximity of points. That is, if 2 points x and y that you sample from the metric space are close, let's say they have distance less than some threshold r, then you add this to your graph. And now the question that remains is, why do we expect this to possibly break the square root n barrier? So, one thing to note about these kinds of models, which are geometrically conscious, is if I tell you a vertex v, and I also tell you that v has an edge to u and v also has an edge to w, then condition on this event that v has an edge to u and w, the probability that u and w have an edge gets greatly boosted. That is, two neighbors of v are much more likely to have an edge than two random vertices in the graph. And in all the models that we considered before, conditioning on edges uv and vw did not boost the probability at all. And that was, in some sense, the thing that led to the square root n barrier. Okay, so this metric space idea is basically trying to um, make the links more densely connected, and hence, and we're hoping that doing this would actually lead to expansion. But the question is, what metric space should one use? And in the choice of the metric space, we draw inspiration from the study of manifolds. So one notion in the study of surfaces and manifolds is that of curvature. I'm not going to get into what a manifold is, but informally, you should think of a manifold as just being like some sort of surface, such as maybe the sphere or torus or Euclidean space. But anyway, the notion of curvature is sort of measures how quickly do straight lines emanating from a point separate. So here's three possible scenarios that could happen. So say you are at a point and then you choose two straight lines. Let's say they separate at a constant rate. Note that this happens if you're in Euclidean space. Then we call that zero curvature. Another situation that could happen is when you start walking away from a point, the rate at which they separate actually goes down. So this is something that happens, say, on the surface of the sphere. When two lines emanate from a point, the speed at which they separate goes down, and then they eventually actually come back and meet each other. So we call this mode as positive curvature. And yet another mode is if two lines leave a point, but then they actually separate from each other at a faster and faster rate. And we call this negative curvature. And an example of a negatively curved space is, say, a hyperbolic space. And there is a certain local to global principle for these manifolds. And in particular, it says that if a manifold is positively curved, then the uh, a certain continuous time random walk on the manifold, some kind of Brownian motion, mixes rapidly. And this is a kind of local to global principle because it's saying that if you locally have curvature at every point, if you locally have positive curvature at every point, then this implies global expansion. Okay, so given that we want to take inspiration from this, the most natural manifold to use is the unit sphere, and we could hope that sampling a bunch of points actually discretizes the sphere in some way and maybe preserves this local to global property where local curvature implies global expansion. So let's now explicitly articulate what a concrete random model for two-dimensional expanders could be. So think of the model where you sample n points, v1 through vn, independently and uniformly from the surface of the unit sphere. And then you connect two vertices with an edge with if their inner product exceeds a certain threshold tau, and tau is chosen so that the edge exists with some desired probability p. Okay, and one thing that I do want to note is that the curvature on the sphere is actually important for the results that we have, which I will get into in the next few slides. And I just want to say that there are certain other metrics that you could try to think of which do not have this positive curvature, such as, say, the shortest path metric in an expander graph or the L infinity metric uh, in a torus. But these actually do not exhibit two-dimensional expansion. That is, the links necessarily have second eigenvalue larger than half if you're using one of these metrics. Okay, so now for the main theorem on the sphere. So if you take a random geometric graph where the average degree is n to the epsilon, where epsilon can be any small constant that you want, and you choose the dimension as order log n, where the constant in front of log n possibly depends on epsilon, then we can actually show that for every vertex, the second eigenvalue of the link is smaller than 1/2 by some constant delta. And this constant delta depends on epsilon. So as you can see, the average degree is n to the epsilon, and all links have second eigenvalue less than 1/2. And due to this trickling down theorem that we talked about, local certificates for global expansion, the whole graph is itself a spectral expander. And just to say a little bit about how we actually analyze this, if you choose a vertex v and you ask what is the structure of the link of v, because that is the graph whose second eigenvalue you would like to analyze, well, the link is itself a random geometric graph inside the spherical cap around v. So you look at all the neighbors of v, they're all uniformly distributed in the spherical cap and independent of each other. And you similarly connect all pairs of vectors which have inner product larger than some threshold. But the main phenomenon that happens is due to concentration of measure, most vectors lie pretty close to the boundary with high probability. And so the link of a vector v is actually reasonably well approximated by uh, a random geometric graph only on the boundary of the cap around v, which in particular is actually a random geometric graph on a certain lower dimensional sphere. So if you want to analyze the second eigenvalue of the link of v, uh, it actually is a question about analyzing the second eigenvalue of random geometric graphs. So now let's talk about what we are actually able to say about the second eigenvalue of random geometric graphs. So if G is a random geometric graph and tau is the threshold for the the threshold that the inner product between two vectors needs to exceed for there to be an edge. Once the average degree is larger than polylog n, the second eigenvalue of the normalized adjacency matrix of G is roughly tau plus a term that goes to 0 with the dimension and the number of vertices. And when we are analyzing the links, we care about a random geometric model on p times n vertices because that's the number of vertices that form a link. And in dimension d minus 1 with a connectivity probability q. And actually the new inner product threshold for the random geometric graph within a link, if once we renormalize, it ends up being this particular number, tau divided by 1 plus tau, which, as you can see, is always less than half. And this is actually the source of why we're able to beat this half threshold. Okay, and now finally to say a little bit about how we actually can prove that the second eigenvalue of the graph is tau. So we do so by relating the second eigenvalue of this random graph to that of a particular deterministic graph. And this deterministic graph is an infinite graph where the vertices are all the vectors on the d-dimensional unit sphere. And you connect two vertices, u and v, with an edge if their inner product exceeds some threshold tau. And actually, for this particular infinite graph, we are able to show that if you do an L-step random walk, then your total variation distance to the uniform distribution decays roughly as tau to the power L. And this decay of at rate tau to the power L is exactly the thing that translates to a bound of tau on the second eigenvalue. Okay, so that wraps up the technical portion of the talk. I want to spend the remaining 1.5 minutes discussing certain further questions. So the first one is, we actually got two-dimensional expanders of degree polynomial in n, albeit a very small polynomial, but we would ideally like to get constant or logarithmic degree two-dimensional expanders. And we know that we cannot get them from the sphere. So what are other manifolds that could possibly give rise to a constant degree two-dimensional expanders? The next question is going beyond two-dimensional expanders, such as say 3, 4, 5-dimensional expanders and so on. We actually suspect that a random geometric graph does say something about these higher dimensional expanders, but our analysis doesn't cleanly generalize. Then finally, you might want to de-randomize this sphere construction, that is, get a deterministic set of points that gives you a construction for two-dimensional expander. And the final question is, does the same result hold for all positive recurve manifolds? Thank you.